Sure, sure. Otherwise, I have it. Maybe I can give it here. All right. So, good morning, everyone, and it's pleasure to be here. Thanks for the invitation to Team TEC. And in next maybe around 18 minutes, I'll be talking about federated learning, which I believe from the telecommunication domain, most of you are familiar with to some extent, if not maybe the entire domain. But I will try to give you some overview. So my background is more towards the engineering and the theory, the foundational aspects of this domain. So in next the few slides, of course, after giving the overview, I'll be talking about some algorithmic aspects as well as some engineering and system related things. So my work is inspired by applications, right? But I don't directly work on applications. So it will be algorithmic and engineering side of the topic. All right. So here we have the a collection of the keywords, so to say, in machine learning, right? We all hear these words in our day-to-day sort of interaction with topics or ideas in machine learning, transformers, LLMs, and everything, right? More or less, this entire ecosystem can be sort of expressed as the following, right? So we have a model, right? So to say, maybe some kind of transformer neural network, right? Maybe SVM, the old school ones, right? And then we have training data. That model is treated with training data, so to say, right? Model is trained. Once it is trained by some process, right? A mathematical algorithm, we have a trained model, and then we use that for inference purpose, right? So our standard, let's say, hey Google kind of applications. So if you ask the practitioners, right, those who are working in industry, you know, so if you talk with someone working in let's say a finance company, right, even though there are foundational models now, LLMs and everything, right, it's not that difficult to find someone who would still vouch for maybe a gradient boosting tree, right, something like XGBoost. So models are okay. There has been a lot of development in the models, right? But what exactly changes the entire game is the training data. The training data is at the core. If you ask a practitioner, it's all the game of data, right? If you have good data, if you have curated data, right, you can get almost any model work to a good extent for your purpose. So it's game of training data, right? Now, training data, of course, needs to be collected, right? Generated training data is not perhaps, going to help us much, right? So training data needs to be collected. Training data collected to data centers, that's okay. But then the collection process also involves, cases like this. So for example, OpenAI, this is like a couple of months old report published in Reuters. OpenAI was sued by someone for copyright infringement. So this is training data collection process. Sam Altman happens to be visiting Delhi exactly a couple of years ago. It was 6th June, if I remember the date correctly, 6th June 2023, when he was at IIIT Delhi, and I was sort of hosting his fireside chat. I asked this question. And of course, around that time, there were entities even in India, NDTV and others, right, who raised this issue that OpenAI had collected data, sort of without giving them sort of credit or the whatever the required process. Okay, so this is one process of data centralization. But then there is a better way, right? So decentralized data, right? So data is available at its sources, different nodes produce data, and then maybe there could be a server which can sort of synchronize among these nodes, right? For this training data. Uh, but why even server? Server has its own problem of failure, right? Why not fully decentralized? So nodes are sort of connected with each other in a peer-to-peer manner, right? It's like a vast network. It is totally scalable. Whoever, wherever wants to join, just join one neighborhood in this entire graph. Okay, so in popular parlance these days, we call it federated data. So we have a server-based model, right? And we have a totally decentralized model, but this is federated. So federated data comes along with some challenges as well, right? For example, data volume, a large amount of data, how to collect that, right? It's not perhaps immediate. Privacy laws, right? Precisely the issue that OpenAI faces from time to time, and then there are reports as such. Um, Data heterogeneity, right? So for example, different nodes may have sort of different data, so to say, let's say different collection of data. For example, some node may be generating more, let's say, when we collect the human, right? Some nodes may be generating data from African places, other places could have mixed population, things like that. So that's data heterogeneity. Unstable networks, of course, we know is perhaps the entire research goes into sort of tackling the instability part. Untrustworthy clients, there could be some malicious players in this ecosystem, and then irregular connections and so forth, right? But at the same time the federated data also brings opportunities along with it, right? So online data, it's like a continuous supply of data, right? It's not as if data is stagnant, that you are training your model in a 2-year old collection of training samples. Real life data, right? It will actually enable us to use, let's say, even our mobile devices to collect actual real life data. Heterogeneous data, heterogeneity brings in challenge, but it is also actually a boon, right? So the thing is that as heterogeneous as your data could be possible, as many samples you can sort of have in your data, your model is as better trained, right? So yeah. And unstoppable data, you just have your system set up, only the system can play something, but nothing else, right? And then large data, of course, dynamic data. So it also brings in challenges. Be that as it may, challenges and opportunities in federated setup. But at the end of the day, telecommunication becomes the foundation of this entire system, right? Of this entire system. So what we can do better is that, because there are challenges in collecting data, but at the same time opportunities in training the model in this vast heterogeneous data. So what we rather do is, on a network sort of setup, right? We train the model at the nodes themselves, at the data sources themselves, train it, and then synchronize the model. Data privacy laws don't allow you to collect the data. Don't collect it. Let the data be proprietary. Let it be trained on their own setup, right? The data sources setup, and then just synchronize the model. That's the idea of federated learning. I mean, in a very high, at a very high level. So please bear with me for some mathematical notations here if you are not perhaps that much okay with this part. But like I said, that I work with algorithms, so I have to sort of present something around that. So roughly, the centralized setup of machine learning can be expressed by this equation on the extreme left, right? So we have a model, and then iteratively we train the model. What is exactly training? The model gets some update in form of gradient. So that is well, I mean, without going into too many details, it's like model updates, right? Iteratively, iteration after iteration, and after a number of iterations, we say that the model is trained. That's the idea of model training in machine learning. In the middle, we have update algorithm for federated learning in a server-based setup. Idea is that this I, the superscript I on the model W, right, indicates a node or a client, right? So the first equation or first relation, so to say, in the middle portion of the slide, indicates that the model is trained locally. Okay, so model is trained, updated, locally at the client itself, ith client. And then what we do, we have a bunch of such clients participating in this tth iteration or tth round, so to say, and then we just average the model. This is the most basic idea in federated learning. One server, right? The server will have the model as w subscript t, and the clients will have model w subscript t comma its k superscript I. Okay. In a fully decentralized setup, there is no server. So of course, each of the clients sort of have their own neighborhood, and in the neighborhood, so as they train the model, they exchange their model state, right, with their neighbors, and then based on their neighbor, there is sort of synchronization. That's fully decentralized federated learning. Okay, so this is the core idea in terms of algorithm, right? And of course, then we are motivated by improving this algorithm in terms of, let's say, if we have unstable networks, then how to tackle that challenge. If we have, let's say, slower connection, how to tackle that challenge. If we have limited bandwidth, how to tackle that challenge, right? So synchronization, of course, is of course a total no in any kind of network. So therefore, asynchronous setup, how to tackle that challenge. So the algorithmic advancement in this domain is motivated by tackling these challenges in the network, the telecommunication network. Okay, then then very quickly, there are like two sort of interesting aspects of this data distribution. So we saw that, okay, there are clients, multiple clients, right, and they will have their data, but data, of course, that way becomes distributed. There are two ways of distribution of data. So a typical machine learning data, regardless of whether it is supervised or unsupervised, has multiple features, right? So here what I have done is that I have expressed, so let's say I have these many samples. So I believe there are roughly maybe 10 or some rows, and then each data sample has these features, right? So roughly maybe 16 or 18 features, for example here. So a typical distribution would be that different clients would have different samples, right? This is called horizontal partitioning of data, and consequently horizontal federated learning. Okay. The other way could be that we have each client having samples, the same samples, but the features are different. So for example, it's very typical in many setups. So for example, I mean, in Austria, where I stayed for roughly 3 years, right? Using our security card, we had sort of data with the health center and then with bank and everyone, and it was very much sort of this kind of a distribution, and they could collaborate among themselves to train some kind of a machine learning model to identify some characteristics of a client. And this is very typical in many other setups in India also. I believe these days credit card companies and banks and other such entities are collaborating among themselves, in this fashion. Okay, so the basic federated averaging algorithm I already talked about, right? This is roughly maybe 8 years old. This word, the terminology which was coined, right? 2016 around, if I remember correctly, in Google. So Google actually used this kind of machine learning model training to train their Google keyboard, right? So this is the first work which everyone cites on federated learning. It was updated a bit. In fact, people found that for heterogeneous setups, this kind of update works much better. Idea is that again, in terms of algorithm, without going into the details, idea is that we also, along with the empirical risk, so to say, in machine learning parlance, right? We also minimize the distance from the centralized model, right, or the synchronized model to the client's model. That's the idea. So this is minimization process algorithmically. So we minimize that. What exactly it does? It actually helps us in checking the client drift, the heterogeneities, tackling the heterogeneity. This is very popularly known as Fed-Prox algorithm. Okay. So then, So then what we did, this is a new work from my lab, right? What we did, we actually generalized the ideas, right? So there are so many algorithms, in the domain of centralized machine learning training. So I have listed down here roughly 47 such sort of combinations of different algorithms. So there are hundreds of algorithms published over, I don't know, last 60 years and so, starting from the basic algorithm called stochastic gradient descent. And then in my group, we actually combined these algorithms and then found that what exists is just surface. And so very interesting and very sort of insightful such ideas can sort of generate performance which was not seen before. And this is our sort of experimental result, right? That we mixed some algorithms which existed before in centralized domain beyond what is now there in federated learning setting, and then we have a very impressive performance improvement. Okay, different data sets here, and along with their results, in almost every case across the benchmarks, we got very interesting results. All right, in machine learning, one more very interesting, topic is causal learning. Okay, so very quickly, maybe I will just cite one example. So what happens when you have let's say fuel price rise, right? Uh, Fuel price rise, it will actually affect the sort of cost to an airline company. But at the same time, airline company cannot base the ticket prices directly that often, right, with changing fuel prices, so that they will have sort of proportionate number of customers. So this kind of, so there is a cause and effect, and in machine learning you cannot perhaps learn directly based on, let's say, the outcome, the ticket cost. You cannot learn maybe what is the fuel price, right, which is just changing the cost to company. Okay, so this kind of setup is called causal learning, and it has its immense applications: finance, healthcare. Let's say you apply, you use some drug, how that drug exactly affects your body, right? Or there are some comorbidities which actually results into death, other things like that, right? So this causal learning played a good role. Okay, so then in causal learning setup also we sort of implemented that in federated learning setting, and then we have very encouraging result. Again, this is a very new work in my lab. Okay, perhaps the first work, to the best of our knowledge, for instrumental variable analysis in federated setup. Okay. Federated trustworthy learning, like I said, that there could be malicious players which can sort of send updates which can destabilize the system. So for that, you need provenance of the updates, right? You need to track how the updates happened, right, over the system. So as we know that blockchain played its own role, starting from the power, the the same seminal, so to say, right, the Bitcoin network, right? And then blockchain is applied to supply chain in all sorts of setup, which I mean, blockchain at this point is for NFT and other popular coins and so forth. Maybe at some point we encounter blockchain based applications. So in federated learning, again, blockchain helps us in keeping provenance of the records. Again, this is a work ongoing in my lab, right? So where every update we record on a blockchain. It gives us trustworthy federated learning. All right. Then, like I said, that telecommunication networks have their own challenges with bandwidth and everything. So we need to also be mindful about which data we should select. It should not be that if we have collection of 1 trillion tokens, then all the tokens have perhaps equal effect in machine learning model training, right? So therefore, we select some data without compromising the accuracy of the model. This is called core set, right? Core set of the training set. So we implemented that in federated setup. In fact, vertical federated learning setup. And this is a paper that is going to appear in this prestigious conference ICML this year. Okay, so I will sort of end my presentation by giving you an overview of what we are doing in my lab at IIIT Delhi. So we are working on a scalable framework for federated learning, where real-time machine learning model training could happen. Right, this framework can be applied for spam filters, for example, in telecommunication setup. Consortium of diagnostic centers can use our framework to perhaps train machine learning model on their data, which they otherwise cannot exchange, right? Real-time agriculture data in rural setup, this framework can be used, right? Then financial model training with private data, you cannot exchange such data, right? And then real-time machine learning model training for policing, even that could be a potential application for our framework. And then decentralized LLM training, avoid the mistakes that OpenAI and others are doing at this point. It has to happen, as people predict, right, that decentralization is the way to go. So yeah, that's roughly my work in the lab. And with that, I invite any question if you have. Thank you.
Why federated data is divided horizontally and vertically? What is the difference? What is the advantage of both?
Okay, sure. So horizontally is natural. You have your, let's say, so Google keyboard, right? As we know that these days Google keyboard is very efficient, right? It has used data in terms of the sentences that we type, right? Over a period of several years. But that is proprietary. The sentence that you type is your own property. Google is not supposed to sort of collect that, right? So so that way, it has to have like collection of data over different clients. That's horizontal partitioning. Like I said, that samples are partitioned horizontally. The other one is vertical partitioning, where the features, maybe let's say the same person, you as a person, is recorded with the government of India by Aadhaar, right? Now let's say you have your health records, you have your financial records, you have your other sorts of interests, right, recorded somewhere else. So person in terms of sort of forming a sample remains the same, right? But the different features of your character of, let's say, your sample in that training data can be partitioned. So for example, bank is not supposed to exchange your data with some gaming company, but they together can train a model. So that's the vertical partitioning. That's the difference. Okay, and both of them have their own applications. Sure.
Yeah, first of all, thank you very much, Bapi, for coming, taking the time. It has been a great collaboration from your team. I mean, we have talked to Raghav was here, Ranjita was here last time, and you are here. Thank you very much. I think mine is not a question, it's just a comment that your work is very important for us. This focus group looks at AI native technologies, and one of the core enablers for us is federated learning. So it allows us to put the machine learning and AI in different parts of the network. It allows us to do the training in different parts, including the edge and the devices. So this is why it is really important. The cost aspect, I mean, in terms of data, core set, especially the core set aspect, we have discussed previously also. The core set aspect is very important for us. It allows us to reduce the data cost,
Yes.
not the dollar cost, but
Yes.
the data cost
Yes.
of this federated learning, especially in the context of AI native. I think that's very good, and let's continue. Thank you very much.
Glad to know. Thanks. Thank you.
Thank you, Professor Bapi, for your insightful presentation. So now I would like to invite Mr. Sabyasachi Mukhopadhyay, AI Lead Tejas Network. So I'll give a very short bio. So he has 28 years of experience in the AI ML field, and he has built multiple scalable AI platforms for different telecom companies, and he has experience in like Ericsson and in Juniper Networks, Cisco, Lucent, HFCL, and very interesting, he is currently pursuing a PhD in generative AI from IIT Hyderabad currently. So his topic of presentation is foundational AI models in telecom systems. So now I would like to invite Sabyasachi Mukhopadhyay.
Hi. Hello. Good morning. It is a pleasure to speak in this forum. So my name is Sabyasachi. I lead the AI activities in Tejas Networks. Tejas Networks is a global telecommunication vendor dealing with equipments in routing, switching, optical, wireless, GPON, and I lead the AI team there. So my topic is foundation models in telecom systems. So I'll start. So basically, what is a foundation model? So if you see, the foundation model was, the term was coined by the Stanford University of Human Sciences, and basically it means that is a machine learning model which is trained on a huge or large amount of data, and it is a very large model and it contains millions of parameters, and the model also can be fine-tuned to the scenario, to any scenario, for better results. So why do we need foundation models? The reason is, in previously always in the typical previous machine learning scenarios or parlances, we used to have to train separate models on various data sets. And that used to take a lot of time and a huge infrastructure to train the model, and it could not be adapted to various domains or workloads seamlessly. For example, suppose in case of our telecom system, suppose you have multiple ports and data is coming from multiple ports to the system. Suppose you want to do forecasting for different ports. So you used to have different models to train the model on different ports with the training data, and it used to take a lot of time. So with these foundation models, the key features are that it can understand broad patterns from massive data sets. It is trained without explicit labels, and it can be easily fine-tuned for specialized tasks, and it offers very good zero-shot or few-shot capabilities. So this is a general flow for foundation models. So basically the foundation models, this is sort of a usage chart. So first there is the input data, and then there is a pre-training with various techniques, and we have a pre-trained model. And with that pre-trained foundation models, we can do either a sort of a zero shot, or we can do a few shot. Zero shot means basically you just place the model as it is, feed the data with the context, it will get a result. Or you can do a few shot, you give a few examples to the model of a particular task, and it will actually forecast, or it will give a result as per the task, or you can fine tune the model as per your specific needs. So as per the industry standards, mostly we currently use zero shot or few shot. Fine tuning on very specialized cases we use the fine tune. So the applications. So in case of the applications, the foundation models can be used in a diverse set of applications. For example, it can be used in natural language processing, in chatbot, summarization, translation. In computer vision, we can do segmentation. In multimodal AI, in predictive analytics, foundation models are playing a key role now. In healthcare, in robotics, automation, creative and generative AI, recommendation systems, across all the domains, the foundation models are playing a very important role. So I will just go over a few applications which we are doing in Tejas networks, typically in the NLP as well as the time series domain, and also we have started some vision related activities now. Now, in the NLP side, we have the chatbot, which is actually talking with a host of agents, and they have several tasks here. We have document search, we have RCA assist, config assist, defect search. So what are the activities here? For example, in the chatbot, suppose you give the information to the agentic systems which are running on foundation models. You can do a config assist. That means if you give an intent, you can you can generate a config from the intent using the foundation models, either in the zero shot mode or in the few shot mode. Again, you can do a defect search. So defect search, basically you have your defect repository, and if you give a sort of an intent or a sort of a trouble statement, you can have a rack system which will have the defect repository. You can give the trouble statement, it can search the defect repository, actually orchestrated as a rack system, and then the output can be passed to a foundation model which can synthesize the output, summarize it, and present it as with the summarization of the defect which is existing. You can do a document search. For example, suppose you have a document repository, you can feed it as a rack system. Rack means retrieval augmented generation. So basically the document can be chunked, vectorized, put into the rack database. You give a document search, it will pull up from the document as a context from the rack system, it will present to the foundation model. The foundation model with the context and the actual query will give you an output, a synthesized, summarized output. This is the use case. In RCA Assist, we can actually use a sort of a graph-based system which can be tied up to the foundation model, and we can get a sort of a analysis of the defects which are currently there, of the root cause of the particular alleviation, any other mechanisms we can use the foundation models. So these are the various use cases we are using the foundation models. As I told, RCA, configuration assistant, generation of configuration, zero shot, few shot, and then defect assistant, finding the defects, duplicate defect reduction, this sort of use cases. Now, a very interesting field is in the foundation models in the forecasting. So previously, when we started the forecasting activity, we always used to use data-dependent models, like for example, LSTMs, or some other models like ARIMA, SARIMA, Prophet, data-dependent models. So what used to happen is that we used to have a data set for a particular system, for example, port, or for example, any other particular system, and we used to train the model. The training used to take long time. LSTMs typically, I remember, I used to train for about like 1 hour, 1.5 hours with huge data sets. And that model is to change for various different ports what we have in the system for doing a forecasting. And also, the forecasting horizon is to be limited. So for example, at the best with LSTM, I used to have like 3 hours, 4 hours, like sort of forecasting. Now with these foundation models in play, we can use a off-the-shelf model, and then we can feed the context to the model, and it can do a long horizon forecasting. For example, we can do a 7 days, 2 months, 3 months forecasting with the context. So some few models which are important, which are coming up as foundation models in forecasting. These are open source models. First one is the closed source, TimeGPT. So these models, they're available off the shelf, and you can actually use those models, give a context, and do a long horizon forecasting on them. For example, TimeGPT is a model which is developed by Nixla. It is a closed source model, but it has a transformer architecture, and it is basically, it understands the order of past events. It is trained over 100 billion data points with various different time data sets of finance, healthcare, weather, IoT. And TimeGPT, it can make very accurate forecast. It has a very long horizon. So I have actually made like 3 to 4 months of forecasting, advanced forecasting with TimeGPT. It also has multivariate capabilities. You can add exogenous variables in order to fine-tune the forecasting better. It also has advanced anomaly detection capabilities. Time MOE is a mixture of experts model. So basically, this foundation model, sometimes it has huge, sometimes the size is big, like suppose 1 GB, 2 GB size, and it takes computational resources. In case of this MOE model, basically there is an array of experts and a few experts can be used to do the forecasting based upon some routing mechanism, and the computational resources shrink. So time MOE is a mixture of experts model. Moirai is a model which has come from Salesforce. So Moirai model, the main capabilities of the model, it is a very good exogenous, inherent native exogenous capabilities. And Moirai is also encoder only model. It is a probabilistic model. And for example, it gives the forecast for 100 samples. You can do a median of that and get a point forecast. And it supports exogenous, and it uses a mixture distribution, and then it has also developed a LOTSA dataset. LOTSA dataset is actually a dataset which is having data from various different 9 foundational models, different domains in time series with a various granularity like seconds, months, years. It has that data set. And then TimesFM. TimesFM is a model which has come from Google. So TimesFM is a point forecasting model, and it is very accurate. It can do a long horizon. It has a restriction of the context. It has 2,400 context points, but it is a decoder-only model, and it can predict longer future sequences in fewer steps. Now, as I told, what is the application? So, for example, we have this foundation model, and we have various domains. We have routing switching, we have manufacturing, we have wireless, GPON, DWDM. So on these various domains, we have various applications which are actually based upon the forecaster, like energy saving in wireless. we have resource optimization, we have resource optimization, failure prediction in manufacturing, capacity planning in GPON, we have power profiling, capacity planning in DWDM, anomaly detection, all these various domains, you can have a single foundation time forecasting model. You can feed the context of the particular data set and it will forecast the horizon you want to. The configuration is extremely simple and there is no training mechanisms involved at the back end. Suppose you do want to use the model for a specific particular data set which is very peculiar, then there is a capability of fine-tuning the model. You need not train the model as the LSTMs we used to do for half an hour, complete all the layers of the model. You can specify a few layers and it will take hardly, let's suppose, few seconds to fine tune the model. In general, the forecasting takes a time period of 1 second to milliseconds. So it is very, very fast, very, very efficient foundation models in this forecasting area. I will present some, basically, some sort of results, what we have for GPON and also wireless. So, for the GPON, we have the use cases as capacity planning, resource allocation, quality of service, cost savings, enhanced decision making. For example, this is the GPON RX octets. So what we have done is we have done a weekly forecast with a 1 hour time granularity. Like for example, we have 168 data points. We are forecasting in advance. And if you see, the accuracy is 85.6% of the weekly forecast. And it all fits within the CI boundary. And the red is the predicted, the blue is the actual. So if you see the pattern, it fairly understands the pattern and is able to do a long horizon forecast. And similarly, on the wireless, we have done a forecasting. We have done the forecasting for this RRC connection attempts, accuracy of 93.96%. It is also fairly accurate. If you see the pattern, the predicted and the actual, it is almost tallying. We also did a sort of a forecasting for a month. We are currently trying 1, 2 months, 3 months forecasting with these foundation models. You can understand the advantage, right? Now, there is also, we are recently embarking on the activity of using the foundation models in image processing. So in the image processing, there are some models which have been come out from Meta. The models are SAM and SAM2. So SAM is actually trained on SA1B data set, 1 million masks. We are trying to find out the masks from this data set. SAM mostly static vision elements, and it is a general purpose segmentation models. SAM2 is sort of a advance on that. So SAM2 basically we can actually segment the video, and the SAM2, the advantage is it is a foundation model, and the advantage is like if you can mask a particular frame, you can divide the video into multiple frames. If you can mask a frame, it can actually repeat across multiple frames and do a video sort of segmentation. So this is the foundation models in image processing, and these are the sort of use cases. So with this image processing application, we can do predictive beam and blockage management. We can identify the blockages in the beams with this segmentation. We can do a localization of the receiver. We can detect the object, do the localization of the receiver. We can do an environmental aware channel estimation. And we can also, the major activity what we are doing is that in the wireless systems, it is sometimes difficult to do processing on the actual system. So what we are doing is we are doing a digital twin where we actually do a simulated systems, and on that we use the SAM model to generate identify the various objects by segmentation. So I would like also to go through a few this thing. So with respect to model size and the model time, so a few models, what we have actually tried several foundation models with respect to forecasting and data dependent models. So for example, first the time GPT. The time GPT, the main thing is it is an API based model, so you need an API to connect to the system. And the typical inference time, as I told, it is very fast, 3 seconds of inference time. Times FM is the Google model, so the inference time is like 7 seconds. It is a bigger model, and Times FM there are two flavors, 200 million parameters. It is size is 814 MB, and Times FM2 is the newer model, 500 million parameters. The size is 2 GB. The Moirai model from Salesforce, the inference time is 1 second, and the Moirai large size is 1.24 GB. So the model is a little bit bigger in size, but as you can understand, you don't need to actually deprecate the model on your thousands or millions of ports what you have and do the forecasting. One model is there. You can do a zero shot. You can have a context. You can do the forecasting on the model. Similarly, on the SAM side also, if you can see, the sizes are in the order of MBs, but the inference time is pretty fast. So yeah, so that is more or less my lecture. So I would ask for any questions.
Uh, yeah. Good morning, and thank you for a very insightful lecture. So, just I was wondering whether this foundational model which you have just introduced to us, how much explainable it is, or how can we compare it to physics-informed AI models, which is talk.
So these transformer-based models are sometimes black box models. So the explainability is sometimes less, but you can always tie it with external tools which can actually help in the explainability. There are external tools which can be used in the explainability. But in general, the time series, from the time series perspective, if you say the time series model, what we normally do is the accuracy with respect to the MAPE scores. So what we check is the actual versus forecasted and the accuracy. So from that metrics perspective, it is pretty good. If you want the explainability additionally, you have to add some extra tools to it and do the explainability. The transform models are typically black box models.
Okay, and then has it got attention of means economics? Is it getting used in economics for understanding the short run and long run dynamics among the time series models? Means
it can be used across any domains.
Okay.
So you give it a time series, it will do the forecasting. Any domains, any horizon, it can be doing the forecasting.
Okay,
So
great.
it is domain independent. That is the main beauty of it.
Thank you, sir.
Excuse. I have a question regarding wireless actually. What I can see, the model is there for forecasting something, say for RRC, this connection attempt plot something.
Right.
So are you planning to use the models or like any other model for optimizing the RAN network also? Are you have any plan for RAN network to be deployed in the field?
Yeah, so in the RAN network, there are various applications, right? So in the RAN network. So for example, let's say energy saving or layer optimization or different applications are there, use cases are there. Each of these use cases has forecasting as sort of a basic pillar element. So the elements from the forecasting will feed into these use cases and these use cases which use the forecasting results to actually implement them. For example, let's say the use case of energy saving. So energy saving, what it does is you try to save the energy by checking how much load is there on the system. So if the forecasted load is going below a particular threshold, you try to switch off the system or transfer the load to some other systems. So the basic pillar of the system is forecasting. So if your forecasting is very good, your energy saving application also will be good. So in RAN, several such applications or use cases essentially use this forecasting as a basic pivotal element. So if you have good forecasting results, automatically all these applications will also come through.
Yeah, excuse me. My question is basic one. Say whatever forecasting models you named, are they not using the old mathematical our understanding like scattering or linear regressions or something to forecast a time series? in the background. This mathematics involved. That's what how the data earlier also used to be forecasted. Actually, isn't
It is a little bit different, I would say. It is not exactly the classical mathematical abstractions what we had. So it is more or less, it is derived from the language-based translation or language-based foundation or the large language models what we have. So language, what is language? Language is nothing but a series of words, and the future of the words, when you do a sort of a generative AI on the language, the future of the word depends upon the past words, the context. Now in the time series also, when you do the forecasting actually depends upon the inherent interdependencies of the time which elements which are there in the past. So these models are actually transformer based models. You feed the time series to the models, you tokenize the time series, you've embedded them, then you feed them into an encoder or decoder model which actually generates the forecast outside. So all these foundational models are mostly transformer based architecture.
so again, but the data or the type of data or whatever precedent data. So it is analyzing in some way in the same fashion to predict the next word or next course or something, isn't it?
It is
so
there.
some mathematics, as earlier Professor Bapi also said, in the mathematics, whatever gradient, say feedback mechanism or something like that, and isn't it? So just wanted to
for the training or pre-training or actually devising these foundation models, you need to have a loss element like MAPE code. You feed it to the transformer elements. It goes into cycle. It generates the model as a MAPE code, and the model comes out. But it is essentially different from the statistical models what we used to have earlier, the ARIMA-SARIMA models.
When you see the models for different applications, the accuracy is varying very big change. How do you set the benchmarking accuracies of that models are concerned?
That is a good question. So for benchmarking the accuracies, we typically use a baseline model, or we use a sort of a naive systems. For example, it can be a seasonal naive. So you take the seasonal parameters, whatever seasonal values was there earlier, you replicate it, and you prepare a baseline system. There are several seasonal baselining systems actually. So you prepare a baseline systems either through the naive methods or through statistical models, and then you check your model how it is performance with respect to the baseline systems.
Sir, forecasting model normally works, but if suppose there is a event, forthcoming event, and if you see the data of the previous month even, so it's all later, there is no much gradient. So data is almost similar. So forecast will be as per the past data, but tomorrow there is an event. So in that case, forecast will be wrong.
So this is also a good question. So these models, they have inherent capability of capturing or taking the events into consideration while doing the forecasting. So you can add historical or future events which you have unknown as an exogenous variable to the model to do the forecasting. So the forecasting becomes accurate.
Period of data to be used to have a forecast should be of bigger period, like year or 2 years or like that.
It can be done. It can be done. Depending upon the aggregation and other things, you can use a large amount of context. Yes. Okay, thanks.
Thank you for a very good presentation, sir. So I'd next like to invite Mr. Kaushik Dey, who is heading the AI/ML research within Ericsson. So brief bio. So he heads the AI/ML research within Ericsson and also leads the 6G for India research program, which aims to incubate the 6G according to needs of the nation. And he has almost 2 decades of experience in Ericsson and IBM across various functions like AI research, product development, and lead realization of key research paper around zero-touch network, adaptive multi-agent frameworks, domain generalization, ultra-low energy AI, etc. and his personal interest is in the field of reinforcement learning, autonomous agents, and agentic frameworks. And he holds 25 international patents, and he's also a PhD degree in computer science from IIT Kharagpur. Thank you. I now invite Mr. Kaushik Dey for his presentation.
Thank you. So thanks for this opportunity to present in this August forum. So I think the previous session, what we had, it kind of leads very nicely into this. So we were talking about generative AI and transformers. So nowadays, what you hear a lot is about agentic AI. You know, you hear about agentic AI, MCP. Nowadays, it's about A2A, Google framework. So all these are what it's dealing with AI agents. What is an AI agent? AI agent, we could think about it's a manifestation of, say, a human capability. It could be in a physical form, it may not be in physical form. So if you have a robot, you know, kind of walking up, serving you a glass of water, it is an AI agent, a physical manifestation of AI agent. If you have AI agent, or say an automated function which is trying to understand where you want to go, what places you want to visit, and then making a complete booking and itinerary for you, that is an AI agent. Similarly, in networks also, there is a huge importance of AI agents. This is still an evolving field. So while I present this, there would be some hypothesis around where we might be going in future. But at the same time, you know, the network presents some unique challenges. It has its unique characteristics. The overall complexity of the network is multifold. You have the BSS, the OSS, the core, the transport, the RAN. The RAN, within RAN itself, you have L1, L2, L3, and within L2 you have probably 10 different functions which you need to optimize. So how does AI agents, you know, fit in the context of network? I will probably try to speak around that part. So before I go there, you know, let us look at how we are evolving as a network. What we were probably around in the stage of manual operations. From there, we can claim that most of the network operators have moved to automated execution. What automated execution in itself means is that we know the task which we have to execute, and then how the task would be executed, you know, that is done by an algorithm. But the task itself is chosen by a human being. From there, what we are going towards is what we call as an intent-based operation. So it's an intent in a sense that we want a network to achieve some high-level tasks, some high-level goals or objectives. How those objectives are translated into the desired KPI goals for each layer, be it the core or the RAN or within RAN each layer, is something that needs to be autonomous. And once it is autonomously selected, then there are algorithms which are also autonomously selected in order to execute that. In order to implement this framework, you know, the agents become very, very important. And while there has been a lot of literature around AI agents, agentic AI over the last 1 year, let me tell you this, that this is not new. You know, the entire LLM paradigm has kind of made this agent word mainstream, which is good, but it was there previously also existing. And probably even in many circumstances, and particularly true in the networks, what we find is that there are different other techniques which could be more suitable for implementing AI agents. When I say that, I mean, as I slowly describe this, remember one slide which Sabyasachi showed. He was showing a latency of, I think, among all the different models he showed a minimum latency of 1 second. Let us make it a little bit more, you know, futuristic. Let's say with the advances in GPU, with the advances in quantization, let's reduce it to 500 milliseconds. Okay, and then we will see where the problem is. Let's, even after we make it better. So now, what we are saying, we are trying to move to a phase of adaptive autonomy. So adaptive autonomy means, given a broader expectation, the network will figure out how to decompose that intent, how to allocate the intent across the various domains of the network, how to orchestrate the different objectives across the network. So imagine you have a simple, like a big kitchen, right? There are somebody cutting a onion, somebody, doing something with the chicken, somebody doing something with mixing a dough or something. All this needs to be coordinated when you are making a pizza. It cannot be that somebody has, chopped off a huge peel of like onions and then the dough is not prepared. The onions will get stale. So there needs to be a coordination. Easier said than done with a pizza example, but it is probably a million times tougher when you are trying to coordinate the how you optimize or how you orchestrate a scheduling in a L2 with respect to how you will set the packet priority in your air interface. So how can that be done? So with that, I mean, intent, I think Professor Chatterjee was also alluding to it, that what is an intent. So intent is an kind of an elaboration of an expectation, a formal specification of an expectation. It could be something like, for the web users or for the URLC users, I want a latency which is less than, say, 20 milliseconds, and I want a packet error rate below a certain limit. So it could be an expectation. Now there could be various intents in the system. So where we are heading towards what we call as an intent management framework, which will manage these different intents, which will coordinate, orchestrate, and optimize the system such that these intents can be fulfilled. This coordination or orchestration optimization has to work across, again, all the layers. So having said that, how does this kind of manifest these intent management functions across various layers? This is a hypothetical example, extremely simplified for the purpose of this broader presentation, broader discussion. So please do not take it literally. So okay, we have the system intent coming in here. Then we have, say for example, what we need to do? We need to do an intent decomposition. The intent decomposition happens at a higher layer. What would be the kind of objective you will allocate to radio or the RAN? What is the kind of objective you allocate to core? Again, in a simplified way, there are many more parts to it. Then once you have allocated an intent to radio, say for example, you have the L1, L2, and L3. What is the kind of a, say, a latency that you want to achieve in the scheduler? What is the kind of power control you want to do in uplink? What is the link? How will you do the link adaptation? What is the admission control that you will do in RAN? So these are the challenges that you have in RAN domain. So here, naturally, what you could presume, that how about having a reasoning agent which can break up the overall goals at the RAN layer into these different components. These different objectives or sub-objectives. And then when you break it down, you could say, I will have different agents fulfill the same, right? Fair enough. Then you have another, say, the core network. Similarly, you could have a reasoning agent and then breaking it down, and then you could have different agents fulfilling the tasks. There is a slight difference, or a significant difference rather, between core and RAN, as we all know. But one of the things I want to point out is the latency. So if we look at the schedulers, the schedulers typically need to operate at less than 10 milliseconds of latency, and some of our researchers would vehemently disagree with me. They would say that it is less than 1 millisecond of latency. So, but okay, if we take 10 milliseconds, let's be liberal and take 10 milliseconds, then how do you push an algorithm which has a latency of 500 milliseconds? Can you? So that there comes one challenge. Secondly, the compute availability. In order to do an inference at the edge, you need a significant compute. What is the kind of compute? What is the amount kind of compute we have in base stations today? The AI compute? Any guesses? The answer is 0. We don't have any kind of AI compute in base stations today. Tomorrow we will have, definitely, in 6G. But the thing is that even when we have compute at the edge, there are two challenges. There is a challenge of memory and again the challenge of latency. So what is the kind of, when you push an LLM, to process all those tokens, even if it is 2000 tokens, do we have the kind of memory? We don't even have, or will we have the kind of memory in the first generation of processors which are going to be incorporated? Probably we will not have even 10 or 20% of that memory. That's the second challenge. Then I don't see it as a challenge, but it's kind of a challenge and a solution. So in view of all these challenges, probably we need to recognize that our systems, the entire network is significantly different from the agentic architecture, what say probably a travel booking site, or say for example some other business processing site which it could have, where it connects one LLM to another LLM to another agent using a lang chain like structure. That may not work. So rather what might work is a more heterogeneous structure where we have different kind of ML agents. Along with, there could be an LLM agents in some cases where it is suitable. And there could be some classical rule-based agents also. It's very unfashionable to say, and particularly for me as an AI researcher, but I must admit the kind of latency which today, even simple rule-based algorithms can achieve for extreme low latency control loops is not something that AI as of now can achieve that. So for simplistic, more deterministic functions, I would rather go for a rule-based setup, kind of encapsulate them as an agent. So now, what we have these different kind of agents. Let's presume we don't have it now. Let's presume we have these different kind of agents, from reinforcement learning to some prediction agents to classical rule-based agents, and all this needs to work in a framework, right? I mean, they cannot operate independently. So there can be some kind of a coordination framework. And then looking to another paths, what we could also do, which is probably possible now in some instances we have done it, is using a combination of RL agents. So sorry for the clicker. So so what we could also do is we could look at the entire technique of reinforcement learning, and we could have multiple RL agents coordinating different optimizations in the network. So there could be one RL agent optimizing a packet priority. There could be another RL agent optimizing, say, a bit rate. And then recall, there are multiple intents. You are not dealing with only one intent in the system. So for all those different intents, there could be multiple such RL agents. As you have multiple such RL agents, these RL agents need to coordinate with each other. So how they coordinate is, one of the ways is what we call as a multi-agent RL framework. Imagine the multi-agent RL framework as a kind of a football game, where individual footballers, say, imagine they're kind of robots, where individual footballers have been taught how to play using reinforcement learning. But if they don't learn to coordinate, you can understand what would be the result. So now using multi-agent RL, we have taught them to coordinate. There are various aspects of multi-agent RL which we do not have the time to go into with respect to whether agents can communicate with each other or whether agents cannot. If the agents cannot communicate with each other, it imposes a restriction, but the advantage is I reduce the overall communication overhead. But we have a few MARL agents, we have prediction agent, and then we have a framework which controls this MARL agent. This framework, which we call as a reasoning agent here, this can kind of orchestrate. And how this will orchestrate is something that we are showing in a demonstration here. There can be various ways of orchestration. We are orchestrating this through a reasoning technique called the AHT. And above this, we have more like a reasoner or a planner agent, which is looking at the different high-level intents. It is breaking it down into RAN and core intents. I think in the demonstration, what we show is only for in the RAN, only for the scheduler. But of course, the RAN is much more broader. Slightly smaller fonts here. Apologies if you can't read it, but this is the next level, kind of peeling the problem for the next level. So what we have now is an intent decomposition. Then say we have multiple intents. One is URLC, then is MIOT, and say for example some conversational video. There are various KPIs. Say for example in core you have a packet loss, latency, KPI, another for MIOT also you have packet loss, and then you have QoE. To control the packet loss, you could modify the packet priority, or you could modify also the bit rate. But these two agents need to be in sync. Now this yellow agent also needs to be in sync with the agent which is controlling the packet priority for the MIOT, right? Otherwise, if you increase the packet priority for URLC, you will implicitly decrease it for MIOT, even if you do not do anything. So these two needs to be in sync. How will they be in sync? Let's ignore the latency for simplicity. That is to multi-agent reinforcement learning. I will skip this in the interest of time, that how it works. But essentially then, what we have is, we have agents for all these different intents, which are working in conjunction. They're taking action on the network environment, and then they're measuring the KPI. They're seeing that how far they are from their intent, how far they are from the goal, and then they're again kind of doing the next round of optimization. Here the critical thing is that agents are both selfish, at the same time they are tuned to for a team game. So they have their own objective, and at the same time they have a global objective which they have to meet. How that is, so this entire framework, if you look at it, so these yellow agents, these form a group what we call as a multi-agent RL group coordinating packet priority. These orange agents form a group which we call as a multi-agent group for maximum bit rate. And then while these three collaborate among each other, these three also collaborate among each other, but overall it is collaborated by another reasoner agent. So because their tasks are now divided. And this division of tasks and then solving the problem, it goes on at each layer of network. So if you look from bottoms up, it's starting at a basic level, then it's aggregated, then finally it's meeting its goal. So this is a I did not get into the mathematical details of multi-agent reinforcement learning, but there are two other aspects after which I will like to end. One is the need for flexibility and adaptability to real world application. I think, gentlemen, I think you were asking the question of what happens if that data is not there in the last month. If I see a new data, that's something that happens often, right? We human beings, we are trained to adjust to new situations based on intuition. So how can we ingrain that intuition into the AI algorithm is something we call as a generalizability. Now, where are we with respect to generalizability of AI algorithms? We are still at basic level, because our algorithms can only perform according to the data which has been shown to them. New data distributions which they are not aware of, that's something we call generalize. We have limited capability to do that. Now, having said that, okay, there is another challenge. What happens when the resources are scarce? All this, resource sharing works very well when the resources are enough. But resources are never enough, right? So what happens? So at that time, my entire system should be able to understand which is a high priority application. That priority might be given by the human being, or it could be supplied by the system. And accordingly, these agents must learn, autonomous agent must learn how to trade off. That, okay, I will give up my resources so that another agent can consume it. That will enable a critical service to meet its KPI. So this is something the system must have, and there is a way also of implementing it using techniques like multi-agent. Now, what happens when the environment changes? This is the generalizability. There has been some progress with respect to generalizability. So I think in the demo also we are showing that what that sum means. However, achieving full-scale generalizability is still probably number of years ahead. There is a lot of debate on what that number of years is. Some say it is 5, some say it is 20. But when we achieve the AGI, we have kind of made the agents as intelligent as human beings. So in nutshell, what I would say is that even though, first of all, LLMs or transformers will become also important in networks, but their applicability has to be rightly chosen. The network will consist of an heterogeneous agentic structure, in my view, rather than a fully, like an all LLM kind of structure. That may not work in the network. At a time when multiple LLMs, if you operate, it will give rise to non-stationarity, which is probably possible for today an RL agent to handle, but the advancement of the capability of LLMs to handle non-stationarity is limited. Non-stationarity means I am doing something, another guy is doing something, he doesn't know what I will be doing, so it introduces an element of uncertainty. Finally, we must be aware about the challenges in the network with respect to compute and inference when selecting the right kind of agents. And then probably the heterogeneous structure is something that works best for our networks. So having said that, I want to thank you for this opportunity to present. It may be a rushed presentation, but hopefully some views have been conveyed. Please,
Kaushik Dey, sir, here.
Sorry. Yes.
Have you identified some standardization gap in it? Means use of agents will definitely require interoperability protocols, and it may have some interoperability issues.
Yeah, I will supplement this question actually. Are you thinking of having any benchmarking framework for these GenAI models to be used in telecommunication networks?
First of all, we are still evaluating where GenAI frameworks can be used. It can be used in higher layers, but in the lower layers, whether GenAI framework can be used or not, this itself is a question. So we are not at a point where we can, profess that yes, a GenAI framework will be used. So the question of putting it in standardization will come later, at a later point, after we have used it. We as of now, we just know the constraints which it has. With respect to other models, there could be some standardization implications also, but many of this work could also be in the proprietary space with respect to how it implements a certain functionality. So it's not so much about how you kind of shared the data between two vendors. It's more about, given a certain vendor system, it will have its own intent. There is a lot of standardization work around intent. So that's what will happen in a separate context. But once you have the intent for the system, how will you optimize the intent in a situation where there could be conflicting intents, in a situation where if you manage the intents using agents, there could be non-stationarity. So how do you deal with it? Also considering that you have the latency requirement of milliseconds in which you have to satisfy it.
I would like to
add for the standardization. Actually, we
Sorry,
have, yes,
yeah,
myself,
please.
yes, VK Roy. Actually, we have standard I2T Y.3172. So from intent, orchestration and management, everything is there, underlay network, overlay network, sandbox, everything is there. Actually, erection and all, if we go for the adoption of that standard, I think it's not a difficult task. So rather, we should go for that.
Absolutely, I
And India
agree with
has contributed much in those standards. Okay, so I think a standard is possible. Beside this, my question is the final target is the autonomous adaptive network. Okay, and that multi-RL.
Yeah, I'll just respond to your
Yes.
first comment. So, of course, I mean, standardization in intents is ongoing. This needs to happen, and we are also supporting it in a big way. So, with respect to agents, my point of view was this is more on the proprietary world. So, standardization is possible, but may not be needed in all circumstances.
Step by step, proprietary.
Yeah, I
where
mean-
it is not possible at all, there is no question. But where some common things where we can have this thing.
Right,
for
of course.
transparency
So, we
and
have to
all.
identify what the
Yes,
common
yes,
objectives.
So
Yeah, please, your
coordination
second
is
question.
required for that. And in final, I think final aim is to have adaptive autonomous network.
Exactly.
Okay. So in multi-agent RL coordination, orchestration and management, the challenge is for all agents have self and global goal. So I think the conflict resolution is the most important thing. So how do you think that this is going to be done and this is being done? I think
Okay,
conflict
so
resolution.
I will probably go a little bit technical, at this point to answer the, yeah. So what you have is, or let me explain through an example. Let's say a football game, right? Now, if a center player in the center of the field, he is rushing towards the opponent goal, you also need the left flank and the right flank to also go forward, right? Now, this is not told, right? When the guy is running with the ball, the center forward, he doesn't shout to the left and the right half that you also run. How it happens is they're pre-coordinated. So they have played many games like this. The coach has trained them that when this guy runs forward, you also have to run forward. That is one way. This is what, and this epitomizes what we call as a centralized training and decentralized execution. In a centralized training in a lab setting, we give, since it's a lab setting, we can give a total observability to all the agents with respect to their how each of the action is contributing towards fulfillment of a global goal. Now, what that helps to set a kind of a coordination mechanism where in the production, in live networks, they need not communicate with each other, but since they're trained to communicate, they will act in a way which is cohesive. So that is one centralized quad. There is another thing which is called, centralized training or centralized execution. The centralized execution is slightly easier, where agents could be conditioned on another agent's behavior, another agent's action. The challenge with that is if you have n agents, then you have, the amount of communication that you need to do, it increases exponentially. So we try to avoid that for network. There are some circumstances where that could be more effective, but generally centralized training CTDE framework are more effective. And in terms of handling such conflicts and in terms of at the same time doing the coordination.
Yeah, thank you so much.
yeah,
So can we take
Amit.
questions during break? We have one more presentation to go, actually.
Okay.
Yeah. Yeah, thank you so much.
Thank you. Thanks.
Thank you, sir, for the presentation. Now I would like to invite Mr. Ajay Kumar, scientist at CDOT, for a presentation. And short bio, he has been working in the field of AI/ML for 25 years, and he has developed intelligent systems that learn and adapt from the data. And he has expertise in deep learning, computer vision, and NLP. So now I'd like to invite Mr. Ajay Kumar. Thank you.
Good morning, everyone. Yeah, I will be presenting to you the Astra solution that is a mandated project given by DOT to CDOT, and we are the implementers. So Astra is AI and facial recognition powered solution for telecom SIM subscriber verification. So there are, it is a quite long name. So there are some points to be noted here that it is a proactive tool. So before a fraud is committed, so we are trying to detect the frauds, and it is an AIML tool, and it is generating intelligence which is helping some other stakeholders like LEAs also in tackling those frauds. So indirectly we are targeting the base, which is the SIM cards. So most of the cyber crimes are being done using the telecommunication resources, using the SIM cards. So we are trying to find out whether the SIM card is a genuine one or whether it has been taken on fake or forged documents. So first I will talk about the menace of cyber frauds and crimes. So this is one of the surveys done by local circles, and it is saying that 47% of urban Indian households surveyed confirm experiencing one or more financial frauds in last 3 years. So considering the population of India, India being number one in the world, 47% is a huge number. So those many people are experiencing financial frauds, and I'm sure many of the people in this hall, they must have got some fake call, or you can say fake email. So recently I got an email from claiming to be from CBI. So at first I was really frightened to see that email, but when I saw its email sender, so it was from a Gmail ID, so it was not an official one. So you can only imagine, if I am working in this area and I got frightened, what can be, what would have happened to a normal person. So similarly, I got a call also, and somehow I was convinced. These fraudsters are so convincing. So he claimed that something is going against you. So later I realized that it might have been a fraudulent call. So just I want to say that it is a menace that is going on these days, and it has to be tackled. And one of the way of tackling it, targeting at the root of it, that is we are doing through Astra project. So this is another clipping from Business Standard. So online scams drain rupees 4245 crore in just 10 months. So it is a 2025 data, and it is also affecting the economy of country as a whole. So again I'm emphasizing that these frauds must be stopped. So at the center stage is the fraud, and I will be talking about the financial fraud. So these are some of the common financial frauds, like fake SIM cards. So this is the one which I will be talking about. So fraudsters are able to get the SIM cards in someone other's names, using someone other's demographic details like name, father's name, address, date of birth, and using someone else's image also. So I will show you some of the collages where hundreds of SIM cards are taken using the same image. And there is a SIM swap fraud, in which the fraudster somehow convinces the TSP that he is the genuine user, and he gets the SIM card issued in his name. And all the OTPs, SMSs, calls will reach him, and he can easily use those OTPs to change the passwords of the bank, and he can easily do frauds. Phishing is another common fraud, where an email will come to you and claiming to be genuine one, and you will somehow disclose your secret information like credit card information or OTPs or other bank account numbers on those emails. So phishing is another kind of fraud, where voice call will come and he will claim to be a genuine party, and you will disclose on the call itself your critical information. And spoofing frauds are those where caller ID is manipulated, and it is claiming to be from a genuine one, and email address is also claiming to be a genuine one, but you somehow don't realize it and fall its prey. So these are another instances where some SMSs are coming from some SBI, and but link doesn't belong to SBI. So you click on this link and you may get into some trap. So these are some of the cybercrime hotspots. So cheating in the name of customer care. So gangs are present in Bharatpur and Alwar in Rajasthan, Mewat in Haryana, and then Noida. So ATM fraud gangs are operational in Mewat and Bihar, which is Jamtara. Fake links and OTP frauds are happening in Jamtara district, and social media kind of frauds are being concentrated in Delhi, Noida. Video calling frauds, these are being done in Alwar, Bharatpur, and again Mewat in Haryana. So this is the financial fraud cycle. So SIM is taken on third party document. So they forge the document like Aadhaar card, POI and POA documents, proof of identity and proof of address, and they use this to get the SIM cards. Then they open the mule bank accounts or some Paytm wallets, and they will then impersonate using and will try to attack the victim through phishing, wishing, or other means, SMSing also. And once they get the credentials, they will do financial frauds, and it will be diverted to multiple bank accounts and it will be taken. So this is the financial fraud cycle, and at the top of it is the SIM card through which this is being done. So we are trying to break this chain by detecting the fraudulent SIM cards. So here, even if there is some investigation, so the actual fraudsters will not be caught because he is anonymous. He is using someone else's POI and PO documents. He is using someone else's image. So even if someone is caught, he will be someone different, not the fraudsters. So untraceability is there, and these are trans-border syndicates, and 70% cases which are currently under investigation, and less than 5% they are that is the conviction rate. So so there arises the need to tackle this fake SIM frauds. So according to a study, cybercrime will cost the world around $17.65 trillion annually by this year. So it is a huge number. So these are some of the fake POI and POA documents. So in the first case, you can see the Aadhaar number is same, but the name is different. Image is same. So here is Jutika Sarkar and here is Subala Sarkar. So in the bottom three fake documents, the name is same, the image is same, but he has forged the Aadhaar number. So these are also fake documents. But using these fake documents, they are able to get the SIM cards. So this is the misuse of telecom resources. So telecom resources are a very prominent source for making these frauds. So syndicates are creating fake POI, PO documents. They are constantly changing their name. They are using someone else's father's name, date of birth, address, or other KYC details. Then they reuse same image, and often they are also disguised, like they are using some chunnis. The male, sometimes he is posing as male, sometimes he is posing as female also. And then earlier there was conventional text-based analytics was done. So only subscriber details records were analyzed, and when looking at the subscriber detail records, you can only see that these are all genuine ones. You cannot tell whether they are related or not. But when image is combined with it, so you come to know that same image is used with all those connections. So in that case, the fraud was caught. So this is the proactive AI-powered digital intelligence tool. So it is detecting and weeding out the fake SIMs before used for cybercrimes. Second is prevention of cybercrimes and frauds, because if you are removing the SIM cards, fake SIM cards from the system, then obviously cybercrimes will be reduced, and it is then catalyzing the investigation of cybercrimes. So we are also generating intelligence regarding the POS agents, point of sale agents, and sharing with the LEAs also, so that they could file the FIR against them. So this is a face comparison that we are doing. So the basic technology we are using is face recognition and face clustering. Along with it, we are using the fuzzy logic for the text relationship. So for example, two names are there, Naveen and Naveen. So they will be categorized as one single name. That is a fuzzy logic. And by using SIM verification tool, at least 1000 times the SIM verification has increased. So, and now Astra is agnostic to these fake POI and POI documents. So we are detecting the fraud because by detecting that same image is used, but different names are used. For example, his name may be different, his father name may be different, he may be using different date of birth or different address. So if his demographic details is changing but image is same, then we are claiming that it is a fraud. Similarly, if individual subscribers, in case there is a limit on getting the number of connections. So in India it is 9. So if we detect any number of connections to be more than 9 in a particular set of collage, then we claim that it is a fraud. So this is one of the sample cases of fraud. So here the person is posing as male as well as female, and we are detecting him as a one person. He has taken 7 SIM cards. He has used 3 names. So this is a confirmed fraud. In this case, he has taken 52 SIM cards in his name, using 25 different names, both male as well as female, and Astra detects it as one fraud. So this is the same image being used for taking 213 SIMs across different DSPs, and they have used 100 different names, using 100 different forged or fake documents. So Astra detects it as one fraud. So there are numerous examples where even we have generated 1000 images collages also. So, and often the POS are involved in it. So it cannot be done without the involvement or collusion of POS. So we are generating intelligence about those POS and also sharing with the LEAs. So these are some of the stats. So we have analyzed total 134 crore connections, and detected suspect connections approximately 81 lakh, and TSPs have disconnected 77 lakh after re-verification, and POS agents who are blacklisted are 71,000 so far. Total FIRs registered are 365, and total number of POS who are mentioned in these FIRs are 1,890. So this is another sample example where 100 SIMs are taken using 76 different names. So these are some of the POS analysis. So on the left side we have POS who are selling more than 5 fake SIMs, and on the right side we have POS selling more than 10 fake SIMs. So you can see that the concentration of those POS, they are lying in mostly in West Bengal. It is a highly dark area. So both in the case of 5 as well as 10 fake SIM cards, West Bengal is the hotspot. So this is an impact of Astra. So in Mewat area earlier there were 5 lakh fake SIM cards, and it was reduced to 65 fake SIM cards in just 1 year. So that is the impact, and it is there in the news. This is another application of Astra. It was used during Balasore train accident, where around more than 80 bodies, they were unclaimed bodies, and they were highly disfigured also. So DOT approached us, and we tried to find out, and approximately all those 80 bodies we could find out their SDRs, their address, their mobile numbers, and shared with the LEAs, share with the, and also the disaster relief agencies. Yeah, these are some of the awards that we have won. So we have won the 8th E-Northeast Award 23 for Astra. We have won 14th Aegis Graham Bell Award 24 for Astra. We have won Alcina Definition Award 24 for Astra. These are some of the news clippings about the Astra. You can go through these. Yeah. Then it is related with the AI, the concept of responsible AI. So I call responsible AI with the acronym of FAP. So FAP is the fairness, it is the explainability, and it is the privacy. So every AI system must be responsible. AI, as you know, is imitating the human behavior, and human, as you know, can be responsible as well as irresponsible. So in the same way, AI can be responsible as well as irresponsible. So we have to make a responsible AI solution. So what I mean by responsible, I will cover the fairness example. So there was a situation in 2021, someone searched the ugliest language in India, so in the Google search engine, and it resulted as Kannada was the ugliest language in India. It was in 2021. So this caused really the widespread outrage in Karnataka, because how can it be a ugliest language in India? So Google then, how did this happen? So Google algorithm aggregated user-generated content from forums and blogs. So it got all the data for training from the net, be it blogs or somewhere else. And they were not authenticated feedbacks. They were users' general feedback. So some bias was there in that content, and Google did not realize, and it trained its model using that data. So hence that kind of the answer resulted. So public reaction was obvious. So it was a massive backlash on social media, and Karnataka government also demanded an apology and explanation. Citizens were protesting. So what was the Google response? First, it apologized and removed the offensive search result. Then Google acknowledged the importance of cultural sensitivity. So here I would like to stress upon this one aspect, the cultural sensitivity. The models are being created in the West. They are trained on their model. They may not work here on Indian culture, or may not work in some other culture. So they have to be trained on Indian data. They cannot be directly used. So this is a prominent example of that problem. So Astras, we have also used our face recognition models. We are actually trying to improve those face recognition models using Indian images. So still there are problems regarding the people who are present in, say, Rajasthan or Punjab. The Western models is not trained according to those faces. So we are not claiming 100% accuracy, but we are claiming approximately 98% accuracy right now, and in the process of training our own model. So these are the key takeaways. AI and search algorithms can amplify biases from online content. So what I can say is algorithm is not bad. Algorithm is always good, but the data with which it is trained, that is good or bad. So the data cleaning is a must before training any AI model. So cultural sensitivity is crucial. So it has to be taken care, and then companies must implement better oversight. Yeah, they must recheck before making their models or solutions public. Yeah, thank you. Yeah, any questions?
So thank you, Mr. Ajay Kumar, for your presentation on Astra. So now, as a token of gratitude and respect for all the speakers and their technical topics, I would like to request Shri Dev Kumar Chakrabarti sir, member designate, to come to the dais for presenting the mementos to the esteemed speakers. And I like to call the speakers also one by one. Okay. So you can. So I'd like to call Shri Bapi Chatterjee first. Next, I would invite Mr. Sachi Mukhopadhyay to next, I invite Mr. Kaushik Dey to take his memento. Next, I would like to invite Mr. Ajay Kumar to please take his memento. So now the technical session is now closed, and I request all the dignitaries and the participants to proceed for high tea. We will be starting the next focus group on AINN working group 2 meeting sharp at 11:30 in this hall. Thank you.